We've all seen the headlines: new study proves, groundbreaking research finds. But how do you know if a study is actually good? Like, trustworthy, fair, and based on solid science? Because not all research is created equal. Some studies are smart, well designed, and honest, others, not so much. In this video, I'm going to show you 5 simple things that can help you spot the differences so you don't get tricked by bad data dressed up like science. These 5 stats will change the way you read headlines, share articles, or even trust what your doctor tells you. To a brand new diet pill worked, but then you found out that the study was only done on 20 people. Would you trust it? Here's the problem: small studies can be way off, like rolling a dice just once and thinking 6 is the most common number. You just don't have enough information to know what's really going on. That's why the FDA, the guys who approve new medicines, say you need at least 3,000 people in a weight loss drug trial before you can say it's safe. And half of those people need to be followed for a full year. Why? Because rare side effects might only show up in 1 out of 500 people. You need enough data to prove the results weren't just random. And because if we want a drug that works for everyone, we need to test it on all kinds of people. Here's the official source right from the FDA's rulebook. So let's say a study does have a good sample size, thousands of people. That's great. But here's the next thing to ask: how did they decide it actually worked? You've probably heard the phrase, the results were statistically significant, with a p value less than 0.05. That sounds fancy. It feels like a green light. But here's the truth: most people don't know, even a lot of researchers. A small p value doesn't mean the result is true. It just means it was unlikely to happen by chance. And yet, people often treat it like a stamp of approval. If it's under 0.05, they say the study worked. If it's over, they toss it out. That's a problem, and we've got stats to prove it. A medical textbook summarized 2 major reviews of published research. They found that studies misinterpreted p-values. Even worse, a separate study found that only 41% of medical residents, these are the people training to be doctors, could correctly explain what a p-value means. And only 1 in 5 understood how to use confidence intervals. That's a huge gap in understanding. And it's not just academic, it affects real-world decisions about medicine, policy, and public trust. So what should you take away from this? When a study says something is statistically significant, ask a few more questions. How big was the effect? Was it repeated in another study? And does it actually matter in real life? Because statistical significance is just the beginning, not the full story. So we've talked about sample size, we've talked about p-values. Now let's talk about the stuff you don't see, the research that gets buried, hidden, or ignored. Here's the truth: studies that find nothing happened often never get published. Yep, if the results weren't dramatic, or didn't show a big effect, or didn't hit that magic p-value less than 0.05, a lot of those studies end up in a metaphorical drawer. That's what scientists call publication bias, also known as the file drawer problem. And it's a big deal. A 2023 review looked at hundreds of studies, and it found that up to 75% of them changed their plans. They either left out the results or swapped what they were supposed to report. Why? Because the original results didn't look impressive. That means what we see in journals and the headlines that come from them are only part of the story, the flashy part, the positive part. But science isn't just made of breakthroughs, it's also made of we tested it and it didn't work. And that's just as important. Here's why this matters. If we only publish the exciting stuff and ignore the boring or null results, then we get a distorted view of what's true. It's like flipping a coin 10 times and only showing the flips that land on heads and then saying, wow, this coin always lands on heads. That's not science, that's cherry picking. So, what should you watch out for? When you hear about a bold new study, especially one that seems too good to be true, ask, have other studies found the same thing? Were any negative or inconclusive studies mentioned? Does this result stand out because it's the only one you're seeing? Because real science includes the wins and the strikeouts. Big data requires good data. You have to ensure data quality. We often hear that big data and AI are transforming healthcare, making it smarter and more efficient. But here's the catch: more data doesn't automatically mean better decisions. If the data is biased or flawed, the outcome can be misleading or even harmful. Here's the next stat. In 2019, researchers analyzed a widely used healthcare algorithm designed to identify patients who would benefit from extra care. They discovered that only 17.7% of patients flagged for additional care were Black. However, when the algorithm was adjusted to remove bias, that number jumped to 46.5%. This means that the algorithm was significantly underestimating the needs of Black patients. Why did this happen? The algorithm predicted healthcare needs based on past healthcare costs. But here's the problem: Black patients often incur lower healthcare costs, not because they're healthier, but because they have less access to care. So the algorithm mistakenly assumed they needed less help. Why does this matter? This isn't just a technical glitch, it's a real world issue affecting who gets care. When algorithms are trained on biased data, they can perpetuate existing inequalities. So, what can we do? Question the data. Where does it come from? Does it represent everyone fairly? Audit algorithms. Regularly check for bias and adjust as needed. Promote transparency. Understand how decisions are made and who they affect. Because big data should lead to better care for everyone, not just those who are already well served. All right, we've talked about p values and how they can be confusing or even misleading. So, what should we look at instead? Try this: confidence intervals. So, what's that? A confidence interval is just a range. It tells you how sure the researchers are about their result. Let's say a study says a new drug lowers blood pressure by 5 points. If the confidence interval says 2 to 8 points, that means the real answer is probably somewhere between 2 and 8. That's helpful. It tells you how big the effect might be and how much wiggle room there is. A p value just says yes or no, but a confidence interval says here's what we think is actually happening. A study in 2024 looked at a bunch of medical trials. They found that most studies didn't fully explain their confidence intervals, and many had changes between what they had planned to study and what they actually published. So, not only were confidence intervals underused, researchers were also changing the story after the fact. So, why does it matter? If you only look at p values, you're missing the big picture. Confidence intervals show how solid the results are. If the range is super wide, that means we're not very sure. If it's tight, that's a good sign. So, next time you read a study, ask, what is the confidence interval? Is the range big or small? Does it actually mean anything in the real world? Because knowing the size and not just whether it's significant is what really matters. So, what makes a study trustworthy? It's not just about big words or fancy charts, it's about the basics. Did they test enough people? Did they rely only on p values? Did they leave out results they didn't like? Was the data fair and accurate and not biased? And did they show how sure they were using confidence intervals? Good research tells the whole story, not just the parts that sound good. So the next time you see a headline or a new study, ask a few simple questions. How many people were in the study? Did the results actually matter? Was anything left out? Because science isn't about perfection, it's about being honest with the data.